Welcome to my video about causality. This is a re-recording of a talk I gave recently at the Cloud Native Frankfurt meetup, and it's about the mechanism we could build into Kubernetes, which extends the controller pattern everybody knows. The punchline of the topic is every mutation needs a cause. So let's go to the motivation of the topic. And it's inspired by an incident which happened a few weeks ago, and it started with the deployment of a couple of B200 GPU nodes. And if you know this term here, B200, this is basically the most expensive type. So it's about a cluster which has at the end 1,000 nodes of those. And you can imagine if you look into the price list at Amazon, if you run this in AWS, this cluster will cost like $140,000 per hour. So it's really expensive, and everything which goes wrong here has an impact, obviously. So what happened there? Basically, some days before, in the week before the incident, an engineer started to deploy those B200 nodes and started with a small cluster, everything deployed, automated with Terraform. And then a burn-in phase started. So he scaled it up and verified a couple of GPU nodes every single step in this scale-up. And the goal was to get to 1,000 nodes. And when it hit 1,000, this cluster was given to the product team, and they started to use it in production. And the incident was actually a few days later, like the week after. The release team of the platform deployed a new version of a controller, and the controller fixed an issue and it removed the metric server from some clusters where metric server didn't work correctly. But it happened that this production cluster was also targeted by this change, and nobody saw that coming, and the metric server was removed. And automation did what it does, right? It kicked in and started a Terraform reconcile. And now the metric server was removed, so it took the declared state and it removed the metric server, but it also scaled down the 1,000 nodes to less than 100. And the reason was that only the initial replica count was part of the source of truth of Terraform. So there was the manual burn-in happened in the AWS console and was never brought back into the system. So now that we have the inspiration, the incident, let's look a bit behind the scenes. What was the root cause of what happened here? So the system we are using, there's Terraform, and there's some stack of controllers and CRDs running in Kubernetes in front, orchestrating the deployment, the run of Terraform. And like everything in Kubernetes, when you build a system with CRDs, it's a declarative system. So you have a declarative state, and this might differ from the intended state. The intended state was actually not in the system. It was in AWS and done in the console manually. So one root cause was here, of course, this information, like the change of the replica count of the node pool was not brought back into the system. A second root cause you could come up with here, what happened here was that there was drift between declared state and the real system state. And this drift was not escalated. We didn't know that the drift existed. And if you know Kubernetes controllers, how they work, it's not normal that a controller actually understands what drift is and has no understanding of any change, any diff to the declared state. And the third one here is what we saw, like there was a software update, there was a controller update, and software updates can cause drift, unintended changes which are not reflected in the desired state. And the insight I had here after something with Terraform happened, I've worked for Crossplane, for the company behind Crossplane for quite some time. And I realized that this was not actually a Terraform problem. In Crossplane, it would have been exactly the same. And basically, it can happen with any kind of controller in Kubernetes. Whether you use ACK or use Argo CD, any kind of OpenTofu controller-like thing, or the Crow system, which can template out objects in Kubernetes, they are all not aware of the changes they apply. Yeah, and the most painful part maybe, so we try to automate Terraform. We try to automate the bring up of systems and the reconcile and drift correction, everything we have learned to be basically the best practice. But the reaction was actually, the reaction of the organization was stop the automation. Like the automation was harmful, and actually it was. And we have to verify the changes, and humans have to look on the changes before they are automated and applied. Of course, we don't want that, right? So we have to think about how can we protect systems which are running, which are super expensive, and yet have automation in a safe way. So the next step is to look on how Kubernetes systems are built. And there's one thing which is obvious when you have used Kubernetes, there are controller hierarchies. And the first one everybody in Kubernetes sees is the deployment, replica set, and pod, right? And the controller manager, the controller manager is creating or deleting, creating, updating pods, depending on the replica set and the values which are set there. But there are many more hierarchies in Kubernetes on the ecosystem of Kubernetes. One, for example, is when you use crossplane on a Kubernetes cluster, then you have a claim usually, and then there's a XR resource, and eventually there are provider resources, those yellow boxes here at the bottom. And again, there is something in between which defines how all of that works. It's an XRD or a function image. And last but not least, in the Terraform world, you will have some kind of Terraform resource for example, the OpenTofu controller. And some of you will use something like Crow to build higher level APIs on top. But again, you get a hierarchy. So Crow is at the top, the Crow instance of a resource graph definition. This instantiates eventually Terraform objects, and then there are OpenTofu or Terraform modules, which then are turned into cloud resources. So again, a stack. And you see this this row here in the middle, the blue boxes. This is all software, right? It's actually not part of the hierarchy. So it's maybe better to just visualize it in this way. So deployment replica set at the site, there is another source which can cause drift, and then you have pods. Same thing with XRD's functions and the modules from Terraform. Another mechanism in Kubernetes, pretty common for many objects, not everywhere, but for many, is that of generations. So parent objects in such a hierarchy, they have a generation, and the generation is automatically updated inside of the metadata whenever the spec is changed. So when the spec changes, the controller does its thing. It reconciles the children objects, so the blue ones here. And when it's finished to update the children, it will update the status of the parent resource, and part of the status is the observed generation. So it's a number. And when those two numbers here agree, like generation and observed generation, they are equal, then we could call that stable. Like the reconciler has done its work and is in a stable state. And from those two pictures, we can already take a look on types of changes. So why does a controller do some work? Like why does it update an object? And the first one here is intended change. Like when a spec changes, the generation goes one up, and the observed generation is still not equal. This is an expected change because the spec changed, right? The controller should fix that. It should update the children. In the middle here, the red change, that's what we call drift. Generation and observed generation are the same. They're equal in the parent. So nobody asked for a change, but the controller still does something, like it updates or changes a child. And yeah, this is drift, obviously. And there might be a third one, and this could also be called drift. There are kubectl edit. So some user goes and kubectl edits an intermediate object, and we will see trace as a concept in a second. This will create a new trace because it's a new origin. It's not the controller doing something for higher level objects in the hierarchy. It's a user touching something in between. It's a new intent. So coming back to the hierarchy we have seen before. So we took one of them here, one of the examples, the crossplane one, but it does not really matter which one we take. So at the bottom are the cloud resources, and I took one of the most destructive changes you never want to see in a system. The database is recreated. So recreation, which is destructive, so data is gone. And in the example here, assume the claim is unchanged, so the source of truth is not changed, and the cross-plane XR in the middle here is also untouched. So the only reason why such a change could be caused is because the function image, which is part of the composition in crossplane here, this was changed, and there was just some horrible mistake inside of that. So when we go back here to our types of changes, obviously it's the second one. So there is drift caused by software updates, generation and observed generation in all the objects above the yellow ones are equal, so nobody asked for it. So it's an accident. And you could build a trace here. The trace is very short because there is just no origin other than the software. So in the trace, we only have the yellow object, very short trace. But we can go to a much more complex case. So here is the user Bob, and he changes the claim because he wants to, change the database type from MySQL to Postgres, and it's well documented that this kind of change will recreate the database. So Bob does that on the claim, and crossplane goes and updates the crossplane XR. Now the composition, the function is unchanged, so no software update, but crossplane will apply the changes to the lower level objects and recreate the database. It's an intended change, and if you look back here into the types of changes, obviously we have the green case here. But now the trace is much longer, right? So you could imagine the trace would be very interesting if you put that on the yellow object, and it starts with user Bob doing the change on the claim, then crossplane service account does a change on the XR, and eventually crossplane service account does a change on the cloud object. So we can store such a trace on objects, and what I did in the causality implementation, I created an annotation. So every object has an annotation of the last change with this trace in some JSON slice easily put onto the annotation of the object. And another nice idea is, what about just putting it into the audit events as well? So the implementation of causality uses admission, and I will show it in detail later on. And admission can add annotations on audit events. So we can put the same trace, like the same JSON snippet on an event. And when later on you see some incident and you're debugging and you look on the audit event for the database here, it will tell you this was changed, like the data was recreated because Bob did something on the claim and crossplane did the thing on the XR and eventually on the provider object. So by now we have an intuition what drift is or which kind of drifts we can hit in such a system. So you update the deployment, so the highest object in the hierarchy. This is not drift, right? The controller creates a new replica set, and the new replica sets creates pods, and the old one is scaled down and pods are deleted. No drift, obviously. You can have cloud resources changing externally, and if you remember the motivation of the talk or the whole project causality, there was an incident where a human changed something in the cloud console. So this would be such a change. Cloud resources change externally, and the controller eventually updates children, and this might cause a correction of the drift. So this is clearly drift. The user which touches objects in the middle, you will see that very often with Argo CD or similar tools. This happens, and then the controller, like Argo CD, just reverts the change, wipes out the change, and the user is usually unhappy. But it's kind of the purpose of those GitOps pipelines as well. So this is also drift. And the last thing, which was also involved in the incident, so software updates, updating compositions, updating Terraform modules, these kind of changes, rolling out a new controller version, updating Kubernetes maybe, because there are many controllers inside. And the controllers reconcile differently now, and this is also drift. And so in short, drift is controller making changes when nothing requested that change. Another insight here is that Kubernetes, the concepts of Kubernetes, you all know, they lack causality. Like causality is always just very, very local. For one request, the API server will tell you it was this user, right? But you will never know who was the origin in the whole trace, like the whole chain of events who caused something. You can reconstruct that by looking at many audit events and somehow linking them logically, but it's very, very tiresome to do that. So we want to know why something really happened. Who did that? Why did it happen? And one important bit here in the puzzle is you want to look on parent objects, and they might justify a change in the child. So causality is linking every mutation to its cause. So this was the punchline I showed in the beginning. So now let's jump a bit into how can we implement this causality system. So I mentioned admission before. So causality, like the prototype, is built with admission, with a webhook. And so imagine you are inside of this admission webhook, and now you get a request, like a request to change, to delete, or to create a child. And the first question this webhook will ask, who does it change? Like, is this kubectl edit user, like the human doing something? But the actual interesting requests are the controller requests. Like, is the controller which controls this child object, like the controller responsible for the parent and for the children, is this the controller coming in and doing a request? And this is not so easy, actually. And I tried pretty hard to find a way to do that because, for example, the user agent looked like an interesting information, but you don't have access to the user agent, unfortunately. Second idea was to look on managed fields. So you have field owners in Kubernetes in the metadata. And again, you don't have access to the new managed fields. This is only updated after the admission. So I couldn't use that information. So what I came up with is a heuristic. And the heuristic is like that. We are recording spec and status updaters. Like for every request to the spec and every request to a status, we're recording the user. And so in the example, we are recording the spec changes. So the updaters, I call them, the spec updaters. I record them for the child, and you see the user A and user B. And I do the same thing for the parent, for the status. And I intersect those two sets, and the chance is very high. Like if a controller, a user, a service account changes the parent status and the spec of the child, then this is a controller. So user E and user B are ruled out here because they are different users. And this works surprisingly well. Like in most Kubernetes objects, this gives you the controller. In Crossplane, it gives you the controller. It works in most controllers, and no special integration is actually needed. This is pretty universal. But there are some exceptions. So I noticed cluster API, for example. The cluster adopts the infrastructure object. And it adopts it as a controller. And obviously, the cluster is not the one controlling the infrastructure. This is kind of a design mistake, maybe you could call that, in cluster API. So for cluster API, we need something else, maybe some custom logic. So we are still in the admission webhook, and the model that the admission webhook implements is the following. So we know how to understand when it's a controller user. So the request comes in, and here in the first box, we do this intersection check, which we just saw on the slide. So is it a controller? If not, it's a new trace, a new origin of a trace, and we just execute, allow, approve the request. If it's a controller, we want to do more. We want to make use of the knowledge. It's a drift or it's not a drift. So we go here to the right and we look at the parent. And the parent has generation, as we saw earlier. So generation, if it's equal to the observed generation, then we here on the right side, then it's a real drift. One of those cases we have seen. And if they are different, it's an expected request, and we can execute that. So now assume we are on the right side in the case of the drift. And what can we do with that? I mean, the obvious case is we can log that there is a drift. Just information that the system has drift to correct might be of value. And in many setups, a drift might be just some issue, maybe a different system operating on the same data, maybe users not knowing there's automation and they do changes on the site. So logging is one mode, of course. We can think about enforcing either reject or approve. So we can, when it's of a certain kind, we can reject the request and stop the automation. And if it's looking good and it's innocent, it's not disruptive or anything, then we can approve it. We can also put the trace on the object. That's what we have seen, right? Traces on objects. So in every object, we have an annotation, and you can, with one look on the annotations, you can see why was the last change happening. So the full causality chain. And the last thing, we have also seen that we can put it onto audit events in the audit log. And this gives us a nice way to debug when something bad happened and to understand why it happened. All of what we have seen is about KRM. So we are in the Kubernetes ecosystem, and we have Kubernetes objects, CRDs, and everything. And Kausality can solve the KRM side, like everything here from the claim to the provider to Terraform to the Terraform object, it's covered. But the point of this slide is it's not enough. So we need another step, like the last mile in the infrastructure as a code system. So if you have a Terraform controller, Terraform runs, and you know that Terraform does a plan run in the beginning, so it's planning and seeing what is different in the infrastructure, and then it executes in an apply step. And in this mechanism, like planning and apply, we also need causality support, because Terraform can detect whether there's a drift outside in the reality in the cloud resources or not, and it can basically take the trace from causality and extend it with another step. Or it can also, it knows whether there is a cause for a change in inputs. So when the Terraform kind here changes, we know it changes because in the chain there is a reason, like causality. So my point here is we need both. Like the last step, the last mile is not enough, because a software update here at the top, like the crow resource graph definition in my example, or the provider controller, they can cause changes in the inputs of Terraform. And we want to protect against that, right? Because the Terraform controller, its last step here, the last mile, it cannot understand whether the change from the top is actually wanted. On the other hand, the upper part, as we just discussed, is also not enough, because then Terraform wipes everything in the cloud resources. It's also not enough. So we need both at once. Now assume we have both implementations. We have causality, and our infrastructure as a service mechanism also supports causality. And now imagine, so Terraform detects that there is a difference, a non-empty plan. I mean, if it's empty, it's a no-op, no-apply, everything's good, right? If you have the right side here, the plan has content, so there's a difference that Terraform wants to apply. We have to understand, is it drift? And if it's no drift, so it's a real change and the causality chain above has made sure there is a real cause for it, then just update. If there is drift, like it's a drift, which means there is no cause above in the hierarchy, then we can do several things. So some examples here, we mentioned logging already, but maybe we want something more intelligent. We can put the human in the loop. So one idea is to, if you use Slack or Teams or something like that, you can escalate to a human by sending a message, maybe a rich dialogue, which can approve, reject a drift, and it shows what changed, and then the human can decide. But in the era of LLMs, maybe an LLM can decide. So it sees the drift, it sees the difference. Maybe it knows about what happened in the past, like what is normal drift we want to correct. And if it has been, like a drift has been seen many, many times, then there's good chance that we can just correct the drift once again. So now we have a pretty good understanding of the domain, of the problem, and that there might be a solution to implement that via admission webhooks. And so my last slide here before we go into demo, or actually the second last slide. So there is this project I implemented. So it's called Kausality. It's on GitHub, and it's an experimental implementation, and play with it. Just a warning, it's 100% vibe coded, and so there might be issues. But anyway, it looks good. There is a demo inside, an end-to-end test actually, which uses Crossplane and shows that this mechanism works really well with Crossplane. Behind all of what we have talked about, of course, there's some kind of philosophy of operation behind. If you have super expensive systems, the fear might be bigger that you let automation do anything without a human in the loop. So there's this fear part, and on the other hand, there is the promise of drift correction and consistency and compliance and all of that. And this obviously is a spectrum, and depending on the area you're working in, this might be different, right? Maybe for banking, the right side compliance is much more important, and but for a system where super expensive clusters are running and you better leave them alone because they hardly change, then the fear side might be more important. So key takeaways. Declarative is not safe, right? It's not the same thing. Just because you declare something, things might go wrong. And if safety is important for you, then there's a lack in Kubernetes today. One thought, controllers should know about the change types, like the different reasons a change, a drift is corrected. Doesn't exist today. This is something one could add. So causality is a missing concept. Causality in the sense of the trace, so that when you see a lower level change in objects, why did that happen? Where does the reason come from higher in the hierarchy that this change should be done? And the last thing, this is basically the proof here of causality of the project. We can detect drifts, we can understand causality in the KRM world, and we can do that via admission webhooks. So before going into the demo of causality, as last slide here for those of you who want to know how this is implemented, like what is the architecture. So here on the left, we are in the Kubernetes world. So admission sees all requests, and we are installing an admission webhook. This is here, this green box, on parents and children. And there is a causality configuration resource you will see in a demo in a second. And it lists the resources where we install the admission webhook on. And this admission webhook looks for updates and creates, and it can, when there's a request on the child, it can look up the parent and check generation and observe generation. It will update and basically keep updated the annotations. So there's one annotation we have seen already for the trace. It's slice. So it's a JSON string, but it has a slice inside. With users and request ID and name of object, kind of object, those kind of things. And there's also a drift annotation. So the last change was a drift correction, true or false. And there is a small decision framework built in. There is an annotation, decision, allowed, denied, and maybe it's a bit misplaced here. It's actually placed on objects, and it decides about children. So imagine here's also such a decision on the parent, and it allows an update of the child here in this light blue, or it rejects it. And there are some more informations inside that can say it's allowed in this generation, or it's allowed forever. So there's a small policy engine if you want, but this is really just prototyped, and one could think about more powerful, more expressive systems for that. So causality is here, gets the request, looks at the parent, does the logic we have talked about, like the controller, user intersection logic. And there's another arrow here. So when it's drift, it calls out to a webhook backend. And here you can implement logging, you can implement Slack integration or LLMs, whatever you like. Maybe one thought which is interesting as well. This arrow here gives you a new event, like a new way to be triggered in a controller style setup. So if you have controllers in Kubernetes, of course, you can watch objects and get events and do something. We are adding another event. And the point here is this might be valuable for new processes. But it could also be valuable because it's an interesting point in time for large language models, for agents. So think about ways how you could use that. So I switch over to the terminal now, and we see causality in action. So everything I show now is live. So I'm using demo magic to not have to type everything, but it's a live demo, so things can go wrong. So we'll see how the demo goes today. So Act 1. We are setting up causality. I mean, it's an Helm chart, so there's not much magic inside. So it's deployed here, it's running. And I talked about a CRD for policy, for configuration, and this is the causality resource here, kind causality. And it lists just resources in API groups. And there's also a mode inside. And basically, this controls the admission webhook configuration, and it tells the webhook how to react on changes. And we have enforce here. So we will stop crossplane in a second doing things. So apply that to the cluster. And the next thing we are doing here, so I go through that very quickly. We deploy a hierarchy of objects in crossplane. So here at the bottom, you see that. It's a hierarchy of nested compositions. So there is an inference cluster, and there's a GPU cluster, and then there are cloud provider clusters. And because I don't want to wait for cloud resources, and it's a demo, it's just a knob resource. So there's a real Terraform backend running in the providers, but it's not really doing something. But you see the idea here. It's a hierarchy of crossplane controllers, crossplane resources, compositions. So everything is applied, and now we create an instance of the first, of the top level here. So we want an inference cluster. And this is basically the incident which I described in the beginning. We start with 8 B200 nodes, and it's a node pool training, and we even have a trace ticket here, the nice Jira ticket CNF meetup 2026. And it's called LLMD cluster for inference. So when we do that, what happens? Crossplane goes, does its job, and deploys a hierarchy. So there will be a GPU cluster, and there will be a knob resource in a second. And here we see it, they are ready. So the hierarchy now is in place. Next thing is we can already check the trace annotation on the last object on the knob cluster, and you see here there are three different entries. So we know when the last one here, the knob resource is changed, why it was changed, and you also see here the meetup ticket part of the trace. And this will show up in audit logs as well, right? That's what I described earlier. In audit logs, when something happens and you look for a change of a certain field in a knob resource, you can trace back why this happened. So second thing here is we talked about the updaters, like the users updating the spec or the status. And here you see it's just a hash of users because of privacy. I don't want to store user data. Although it's not really consequent because I have the user data here on the trace. So maybe one could do that with the full name. But this is basically a small hash of the user to find out who's the controller later on. All right, so Act 2. Now we reconcile, and we want to have a reconciliation which is expected. So it's not drift, but it's an expected one. And we do something maybe the person in the incident did as well in the beginning, changing the top level object in the hierarchy and changing the replicas. And first of all, we check the generation, so it's stable before we did our change, but here we are patching the object, and we are setting replicas from 8 to 16. And because it's an intended change, crossplane should now apply that. So we can first check, again, is it stable? Is the inference cluster stable? It's stable, which means crossplane has done its work. So Act 3. Now we want to look at a change which is not on the top level object, but we basically simulate what we have seen in the incident with real GPU clusters. So we are going into somewhere in the middle here, and we will basically simulate the scale up to 1,000 nodes. So Act 3, new causal change origin. And what we do here, we are patching the GPU cluster, and we are setting replicas to 1000. And I mean, this is now a change, a new trace starting there, and Crossplane will apply it to the lower level objects, like to the knob resource. So this cluster will scale up now to 1000. And as I said, there's a new trace. So trace is very short now. So we have the case now where it's a fresh trace. And yeah, that's why you only see one object. And you see also here it was done by the Kubernetes admin user, which is my kubectl user here. All right, so updaters, again, now we have a second one. I think it was this one here. It's a Kubernetes admin user plus the controller, which was the first, which was there before. So we've recorded that via admission. But the key part here is if we now look on the higher level object, like the top level one inference cluster, and we look at replicas, and what we expect now is that Kausality stopped this drift correction. So there's still a 16. This is not surprising. But the GPU cluster has 1000. So the GPU cluster is now kind of frozen because there was a drift which is not cleared up yet. So Crossplane couldn't update GPU cluster with the 16 and correct the drift. And yeah, next thing is Crossplane sees the drift, tries to update. And now what we do, we look at the logs. So this is a webhook which just logs. So there's drift detected, you see it here. So it rejected Crossplane updates on the GPU cluster, resetting the 1000 to 16. So drift detected, and now we look at the resolution. How can we make Crossplane be the one in charge again of GPU cluster? So I showed before there is this little approval policy engine thing. So on the parent, on the inference cluster, we are putting a annotation, and so it has an API version, which is here our test demo version, demo group. And we have the kinds. So we are saying basically the inference cluster can change the GPU cluster, anyone, if there are multiple, any of those. And it can do it during the current generation 5. So when we annotate, the admission webhook will basically give up the blocking, the lock on that object, and Crossplane can do its work again. So Crossplane should update now the GPU cluster, and let's give it a bit of time, so 10 seconds. And maybe this would be even real time because Crossplane is that advanced today that it can do that when it sees a change in an object. And now 10 seconds are over. We check, and you see the GPU cluster is now back at 16, not 1000, but 16. But of course, it was an intentional approval here, so we wanted that. In the incident I described in the beginning, this happened by accident. And here in this case, you would have a chance to bring back the 1000 into the hierarchy of objects, and then we would have 1000 here. But for the demo, I just made Crossplane fix the drift. And so deletion. Now we want to clean up our mess here, our hierarchy of objects. Usually it's okay to have any kind of drift during bring up of objects in the cloud. So when you bring up a hierarchy, a new cluster in this example, until it's healthy and ready the first time, usually don't care about what happens, right? And this is what is implemented here as well. And the same happens for deletion. During deletion, you also don't care about drift because everything is destructed anyway. So there's really this phase between healthy bring up, when it's finished, the bring up is finished, and the deletion. This is a time when Kausality should take action and bring us safety back. All right, this is basically all I wanted to say. So it's an admission webhook. It's experimental. Take a look here on the project, and some key takeaways. That's all I wanted to say. Thank you for listening.